Hello, so today we are going to continue on problems from weekly count test 342. The last problem, minimum operations to make all array elements equal to 1. So here we have an array that has positive integers, and we can do one operation any number of times. We can select an index that is between 0 and n minus 1 and replace either the number at that position or at that position plus 1 with the GCD of the value of the two numbers, okay? So we pick two numbers next to each other, we get the GCD, and we can replace one of them with that GCD. We choose which one. And the goal here is to return the minimum number of operations where we can make the numbers in the array equal to 1. If we can't do it, we want to return minus 1, okay? That's pretty much it. So let's take a look at this first example. So this first example here, what we can do is take these two. The GCD is 1. Okay, and so we can replace that one either in this position or this position. Let's say, for example, we choose this position. So we put 1 here. Now it's easy because the GCD of any number with 1 is 1. And so now we just take the GCD with 6 and 1 and we replace the value here with that GCD value, which is 1. We do the same thing here. Now that we have a 1 here, we take the GCD of the 2, it's 1, so we replace it. And then we go back here, we take the GCD of this one and this one, which is 1, and replace this one. And now we have all 1s. Now how many operations did it take us? Well, the first operation to take the GCD of 3 and 4 and get the 1 in the position of 3. And then for the other one, we did 1, 2, 3. We did 3. So 3 plus 1, that's 4 operations. So we put 4 here. So that's roughly the idea. Now, the main thing you can see here is that the length is actually not too big of the array, is 50. So this tells us we should be able to do something that is n squared if we need to. So let's see how we can tackle it. Okay, so how do we handle this? So let's think about, for example, the first example, what happened. So the first example, what happened is that we found numbers where the GCD gave us 1. And once we have 1, we can put it in any position. For example, we decided to put it here. The next iteration was easy. Replace this one, and then replace this one. Okay, so once we find this one, we know that it will only take the number of elements we need minus that number, that count of that number. So here, for example, we have 4 elements. We already put this one to 1, so we have 3 remaining. And so to get this one to propagate it to all of them, we just need n minus 1. Okay? So that's one insight. Now, that's one insight if we don't have any numbers. Or any one. So if we don't have any one value, then what should we do? Well, find a subarray where the GCD, here it was just 2 numbers, but sometimes 2 numbers are not, like, let's say 2, 6, 2 and 6, the GCD is 2. With 3, let's see, GCD of 2 and 3, that's 1, okay? And so sometimes it takes more than just 2 digits, right? So this will give us 1. So if we had an array like this, then we'll first convert this one to 1 and put 1 in whatever position we want. Let's say we put 1 here. And then now it's just about propagating this value, right? And so what's happening here is that if we don't have 1, find a subarray, right, with GCD of 1, and then the rest is easy. Just you place in that position, and once you have a 1, you can propagate it, okay? Now, what if we have multiple 1s already in an array? So let's say, for example, we have 3, 1, 4, 1, 6, something like this. Well, now also it's easy. So we don't need to find a GCD of 1 because we already have them. So we just propagate this one. So that's one operation. We propagate it here. That's one operation. We don't need to propagate to this one because it's already 1 here. And we don't need to propagate to this one. But we don't need to propagate to this one, so 1. So how many we have? We just have 3 operations. So what's this 3 operation? Well, that's actually just the places we need to propagate to, so the number of those minus the number of 1. So it's basically just n minus 2 in this case, because we have 2 ones. And so basically this is the other observation, which is if there are 1s in the array already, then it's just going to be the result, which is the number of operation we need, is just going to be n minus minus what? Minus the number of these ones. So just the count of ones. That's what we saw here with these n minus 2, which is basically just 5 minus 2, which is 3, and that's exactly what we had. Okay? Okay, so now with these 2 observations, with this one it should be easy to do, right? We can just check if there is a 1 in the array, just count the number of ones. If the count is bigger than 0, just return this. And that would be it. We don't need to do anything else. But what if we don't have 1, and so we need to find the subarray to get GCD of 1? So now the question becomes, does it matter which subarray we find, right? In the previous example that I had, where 2, 6, 3, right, maybe 4, 5, 8. Once I find this one, should I continue? Should I find the smaller one? Right? What if we had maybe let's say maybe 2, 3, 2, something like this. Should I pick this one or should I pick this one, for example? Okay, that's a good question, right? Well, the question here is basically, do we need to look for the smallest subarray or not? Well, let's first think about what's the result when we have this case, right? So case 1. What's the result that we should return? Okay, so let's take a look at this example to understand why we need to take the smallest subarray that will get us a GCD of 1. Why is that the case? Well, for example, here we could of course do this one to get a 1 because the GCD of 7 and 3 is 1. The other way to do it is to take the GCD of 3 and 6 is 3, and then the GCD of that with 4, that will give us 1. So this is just 2 possibilities here. So which one is better? Well, let's just count for each one of them. So let's call this one case 1, and this one case 2, and this one case 1. So for case 1, how many operations we will need? Well, we need the operations just to take the GCD of the 2 and put 1 in one of the positions. So let's say we take the GCD of 7 and 3 and put 1 in position 7. And then we start propagating. So 1 operation to put 7, 1, and then we propagate. So 1, 2, 3, 4, 5. Each time we propagate, we put 1 in that position. And so how many did we have to do? 1, 2, 3, 4, 5. Okay? So this basically is how many? It's just n minus 1. Right? Minus the position that we put 1. We will see how we can compute this one here, but the 5 here is just n minus 1. Okay, so what about the second case? So the second case, what do we do? Well, in the second case, we still need to do the same thing where we take the GCD first of these 2. That would be 3, and let's say we put it here. And then we take the GCD of 3 and 4, and that will be 1, and let's say we put it here. So how many operations did we need to do here? Well, we needed to do 2. But what is this 2? It's just the length of the subarray minus 1, right? Because for each pair we do the GCD, and so the number of pairs in an array of length L is just L minus 1. And so the formula actually is L plus 1. And then what do we add again? Well, we already said it's n minus 1. Sorry, this is n minus 1. That's what I meant. N minus 1 here. So basically, how many pairwise GCD values operations did we have to do and then put the result in one of the elements? Well, for each subarray, we need the length of the subarray minus 1 because that's how many pairs we have to do. Okay? So to go back to this case here, we said 2 just to put 1 in this position, and then once we put 1 in that position, then we need to do how many operations to propagate that one? Well, we first need one operation to propagate one here, one operation to propagate one here, and then we propagate it back here, back here, back here. So how many we need? Well, we actually need all the elements in the array just minus this element where we put 1. And so it's n minus 1, which is 5. Right? Which is n minus 1. And so that's actually exactly what's happening here. This is L minus 1. This is n minus 1. And if you look here, this is also n minus 1 because L, the length of the subarray, is 2. Minus 1 gives you 1 here. Okay? So now we know, first we know the formula that we need to return for case 1. We already know the formula that we need to return for case 2. And we know that we need to choose the smallest length subarray because then it will take us less here, right? It's better here to have 2 than to have 3. It's better to have 3 than to have 4, right? Because otherwise the total number of operations will increase. So you see here why we need to pick the smallest length subarray. So let's adjust this here and say find. So now here this is find smallest length subarray. Okay, now the solution is easy. In the first thing we need to do, just check if there is a 1 already. If there is, then nothing else we need to do. We can just return n minus the number of 1s in the array. Now if there is no 1 already, we need to find the smallest subarray where the GCD is 1, and then once we find it, get the length and return this formula. We already have n, it's the length of the array. Now there is some cases where it's not possible to get GCD of 1 no matter what you do, even if you take the GCD of the entire array. So in that case, we just return minus 1. That's what the problem says. And that's pretty much it. This should be, because we would have to find the smallest subarray, we can just try all subarrays. And so if we try all subarrays, what would be the time complexity? It would be O of n squared, okay? And this one, if we're in the first case, we'll just do one operation. So just to do a loop to find the number of 1s, so that would be O of n. But if we're in the second case, we have to do O of n squared. And this should pass fine because the list can go up to length 50. So this should be fine. Yeah, so that's pretty much it. Let's code it up and make sure it passes. Okay, so let's code up what we saw in the overview. So first we said that we need to count the number of 1s in the array. So what do we need there? Well, first let's just get the length of the array. I'm just going to call this A so that it's easier to write. And then we need to count the number of 1s. So the 1s in the array is just if A is equal to 1. Now here we just can get the length of them. You could choose to do count if you want, but I think this is good enough. So if the number of 1s is bigger than 0, so there is at least a 1, then we said we already know the solution is just to return n minus the number of 1s, okay? But otherwise we have to find the smallest length subarray. So we start out with a big length so that any subarray would be smaller than that. The length would be smaller than it. And now we try all subarrays. We just try all of them. And so to do that for J, to be able to do a GCD, you need at least 2 numbers. So we have to go to start from I plus 1. So we have the number at position I and the number at position I plus 1 at least, right? So now we just check the GCD. Now, a simple way to do GCD is we start out with just the element, and then we just do the GCD of the GCD so far and the element at position J. So that way it accumulates, okay? Now, if this is equal to 1, that means, what does that mean? Well, that means this is a possible candidate, right? We found the one we could propagate it, but we don't know if it's the smaller one. And so let's just check if it's the smaller. If it's the smallest one, then we could so we check if the new one is smaller. This is the length of this subarray from I to J, okay? Now at the end, let's call it actually just best length so that it's more representative here. Okay, so at the end, what should we return? Well, we just said it's L minus 1, which is best length minus 1, plus the number of elements minus 1. But this is only if we actually found one, because in some cases there is no GCD equal to 1 at all. So we want to check that there is one, so which means we did set a value here. So we check if it's different than the initial value. Otherwise, if it's not different, that means we didn't find a GCD of 1, and so we can't make all the array elements equal to 1. So in that case, we return minus 1. Yeah, so there is a problem here because we want to update each time the GCD, because the GCD is going to need to be from AI all the way to AJ. And so each time we add a new element in this subarray, we want to count it in our GCD and then check if that GCD is equal to 1. Yeah, so we just need to move this up so that it works properly. Okay, looks good. Let's submit. And that gets passed. That passes our test cases. Now, in terms of time complexity, this loop here happens 2 times, so it's O(n) squared. And then the implementation here is just O of 1 constant. So overall, this piece is O(n) squared. And then this one here is O of n. And so overall, it's just O of n squared time. Now, in terms of space, we are only using this ones list. And then even then we could just do a count here. You could just do that, like a for a in a, if a equal to 1, you could do it like this, to have only one function. So that would be O of 1. And then that's pretty much it. So it's O of 1 space as well. Yeah. Now we could make slight arrangements here. So for the GCD, you could actually just pass with the entire subarray, which in our case here would be I to j, right? So that's the subarray. So in Python, the notation for that would be j plus 1 like this, to indicate that I and j are inclusive. And so if this is equal to 1, then we could do the same thing like this. So this should work fine, right? So if we run this, yeah, we just need to spread the array elements. So we use star for that, and now we can submit, and this passes. Okay. Now, for this case, we have to try all the subarrays to find the best one, right? But we can do this slightly so that we can stop as soon as we find an element. So what we can do instead is try all the length. So instead of going for I and j here, we'll still keep I, which is the starting position like that, but we'll do a loop for the length. Okay, let's call it L in the range. The minimum range we need is 2 to have at least 2 elements to get a GCD, but it can be the GCD of the entire array, so we go up to n. And now this is the starting position, and now we just need I to I plus L. That would be the length. If the GCD of this equal to 1, we don't need to proceed further. We can just return it because the length is 2. If we continue and this loop finishes, then we will get only to 3 or 4 or even more. And then for all the elements at I, they all have the same length of L for one iteration. And so there is no need to try anything else once we find that the GCD is equal to 1, because we know it will be the smallest length. And so that's where here we can actually just return. Okay, so we can just return this, except instead of using the best, we know this length is the best, so we just return it. And then if we exit the loop and we didn't find any subarray with GCD equal to 1, we can just return -1. And this will make it easier. So if we submit, looks like there is one wrong case. Let's see what we did wrong here. So we need to go for L. It definitely needs to go to up to n, because the length can be the entire array. Okay, so if the array length is, let's say here 3, it needs to go up to 3, but in this case it will be only up to 2, because of this stops at n-1 in Python, so we need to do n+1. Cool. Okay, so if we submit now, it passes. Okay. Yeah, I hope this was useful. Please like and subscribe, and see you on the next one. Bye.